garden cart using a force of 100 newtons and the cart moves about 5 meters. Then you can calculate the work done quite easily simply by multiplying force with displacement, and in this case the work done is 100 newtons into 5 meters, that equals 500 joules. However, if you're also given the information that this displacement happened over a period of 10 seconds, then you can calculate the work done every second or per second simply by dividing the total work done, that is 500 joules, by the time taken, that is 10 seconds. Or you have done 50 joules of work every second, which in simple math is an average. So this quantity is what we call power generated due to the force you applied. That is averaging of per second how much work is being done by the force. Another way of looking at this quantity is to say how fast is work getting done. So here you or the force is doing work at the rate of 50 joules per second. But if you had taken 20 seconds to finish the same task, power generated would have been 500 joules divided by 20 seconds or 25 joules per second, or you did work less quickly. So in a more formal way, we say the time rate at which work is done by a force is the power due to the force. So if a force does W joules of work in time delta t, the average power generated by the force in that time interval is given as P average is equal to W upon delta t. Now, in the example above, we calculated the work done per unit time. That is, we know the total work done is 500 joules and it happened in 10 seconds, and therefore the average work done is 50 joules per second. We are not really concerned with the idea that maybe in some time instances within these 10 seconds more work was done, and in some other instances maybe less work was done. So let us complicate things a little bit and say during one tiny fragment of time, that is between 4 seconds and 4.0001 seconds, there was a momentary spike in force you applied, and it was 200 newtons. And the work done in that 0.0001 seconds was 0.01 joules. Then we can say in that very small time interval, the work done on per second basis is work done in 0.0001 seconds, that is 0.01 joules, divided by the time taken, and that equals 100 joules. So you see, the power developed by the force in that short time interval was different from the average power calculated over the entire 10 seconds. So this is where the concept of instantaneous power P becomes relevant. That is, the instantaneous rate of doing work is work done per unit time at any instant of the journey. And how do we define an instant? An instant of time is nothing but a very, very short period of time, much smaller than 0.0001 seconds. In fact, so much smaller that it almost approaches zero. And remember, when we talk of a quantity approaching zero, it is time to start making use of calculus. So here we define the rate of doing work or power at that instant as P is equal to dW upon dt. That is, in some time instant dt, work done is dW, and we call this instant power. So if you like the way I teach, please do give a thumbs up, that'll be helpful, and let's get back to the lesson. So let us say we know the work done by a force as a function of time as W is equal to 3t square plus 1. That is, work done is varying with time, and we are asked to find the instantaneous power at t equal to 3 seconds. Now, let us first understand what exactly is being asked to find. So this essentially means finding what is the work done in that very short time that approaches zero around 3 seconds, and then converting it into work done per unit time. So to calculate the instantaneous power P at t equal to 3 seconds, we will first find the expression for power by taking the time derivative of W with respect to time, that is P is equal to dW upon dt, that equals 6t here. Now to find power developed at t equal to 3 seconds, that we call instantaneous power at t equal to 3 seconds, we get P at 3 seconds is equal to 6 into 3 or 18 joules per second. So in that short time dt, that is approaching 0 around 3 seconds, 18 joules per second of work was done by the force. Also, the SI units of power is joules per second, and since this unit is used so often, it has a special name, that is watt, after James Watt, who made a significant contribution to the rate at which steam engine could do work. So you can say that 1 watt is equal to 1 W is equal to 1 joule per second. Now, if you observe this equation, you can say that work can be expressed as power multiplied by time. And when we deal with electricity, we use this idea quite often, that is kilowatt-hour. Thus, 1 kilowatt-hour is equal to 10 to the power 3 watts into 3600 seconds, that is equal to 3.6 into 10 to the power 6 joules. Now, since this unit appears on our electricity bills, the kilowatt-hour and watts are often associated with electrical units. But you can use this terminology in other examples of power and energy as well. So, if you pick a book from the floor and place it on a table, you can very well say that the work that you have done is, say, 4 into 10 to the power minus 6 kilowatt hour, which is actually nothing but 4 into 10 to the power minus 6 into 10 to the power 3 into 3600 seconds, that equals 14.4 joules. So these are just two ways of presenting the same information. Another way of expressing the rate at which a force does work on an object is in terms of that force and the object's velocity. So if a particle is moving along a straight line and a constant force F acts on it at some angle theta to that line, then this equation becomes P is equal to dW upon dt is equal to F cos theta dx by dt. That is, we have taken the force in the direction of displacement that actually does work and multiplied it with dx, or the displacement, to substitute for dW, or the work done. So this can then be written as P is equal to F cos theta dx upon dt, or P is equal to F cos theta into V, that is velocity, which if we rearrange like this is nothing but the dot product of F and V, or P is equal to F dot V. So power is an important topic within work, energy and power, and if you really want to get a strong grip on this topic, I would suggest you go through the other lessons also in this playlist, which answer most of the questions students have in mind. Also, if you like this lesson, do give it a thumbs up, and I will see you in the next lesson.